The last time that I spoke in this room about this system, I introduced myself as Jim Maltby from Cray, talking about the XMT-2. And we've changed the name, and now it's I work for Yarc Data, talking about the uRiKA appliance. And that it is the same machine. We've added new software layers, new functionality, new programming models, and I think it's a very interesting product. As was pointed out, Yarc Data is the name of the subsidiary. Yarc is not only Cray spelled backwards, but it's the name of one of our router chips, yet another router chip in one of our previous machines. And this joke was thought extremely funny within Cray, so they called it Yarc Data. And the name certainly wasn't taken. And so the idea is that we're looking at a new market with the uRiKA system, and that's the big data market for graph analytics. So first I'll go through a quick introduction to uRiKA and what it actually is. Then I'll go talk about the multi-threading programming model. As you may know about the XMT-2 and certainly the uRiKA, it has a completely different type of processor architecture that has very unique characteristics which make it well-suited for certain tasks. I'll talk about the SPARQL database, which is the core of uRiKA. Just a quick survey. How many people here have heard of the SPARQL language? Not a hand. Okay. I was at the very large database conference, and I asked that same question, and every single hand in the room went up. So it's a database-oriented appliance, but it's a new programming model that I think is very interesting and very useful for big data. So I'll go into some specifics about the appliance, talk about programming that's possible, and then I'll go through some of the use cases we figured out for the machine. Okay. This machine has actually quite a long history, even though the Yarc Data was formed in March of this year. And after that, they came up with the name. The MTA architecture, multi-threaded architecture, was invented by Burton Smith. And the very first machine at San Diego Supercomputer Center was the MTA-1. So the first machine of its kind. That was gallium arsenide, which was very problematic and unreliable. So they moved it to CMOS, and it's called the MTA-2. It's faster, and it was first scalable memory system in a multi-threading system. Then, however, unfortunately, that was a highly custom machine. And so to make it practical, we moved to the XMT-1, which is, we basically integrated the MTA architecture and our standard Cray product line. So we're able to reuse a lot of the engineering effort that goes into our big systems. And so that's x86 and MTA processors together in one system. That was our first prototype, the production model, the XMT-2, the largest shared memory machine in the world, and it is absolutely uniform shared memory, so it's no NUMO worries. And you may be pleased to know, and probably already know, the very first installation was at CSCS in May of last year. And that too, just like the Cascade machine, you had the machine before it was even announced. And so you couldn't even talk about it. So first machine was here. And then finally, in 2012, we have added new software layers and changed the name to uRiKA and moved to an appliance model. And I'll explain more about what that is. However, the most important thing you should know is that it's built on the XT5 infrastructure. We saw some boards from the XT5 in the museum in the machine room just a moment ago. So it uses all of the same hardware and the same software on the service nodes, which is very important to how it works. We just changed the processor. The multi-threading processor, which we call ThreadStorm, current rev is the ThreadStorm 4, fits into an Opteron socket. So if you have an XT5 and you want to convert to a uRiKA, you simply pull out, on a certain number of the boards, you pull out the Opterons, plug in the ThreadStorm 4s, and reload it with the new operating system. So there's quite a bit of commonality, and that's good because we can take advantage of the engineering we've done for the XT5. The rest of the statistics you probably already know. 4 ThreadStorm processors per compute blade, same service and I/O system, everything else. And most importantly, the service nodes are the same Linux user environment they're used to on the XT5 and similar to the XT or the XE6. Okay. The target market for the new uRiKA machine is graph analytics and big data. And here are a number of different places. Graph analytics comes up in a number of fields. Basically, it's the study of data that is inherently graph structured. It is data that cannot be represented in a regular table so efficiently. So sparse matrix calculations are one example that you may know of, but many other in social networking is like Facebook. If you think of the network of people who are Facebook members and all of their friends, it forms a small world graph with a lot of edges. In the intelligence and security field, you have a lot of actors and a lot of connections between them. Telecoms is definitely graph structured. In the life sciences, you have proteins and interactions between proteins. I'll show you one of a use case later about interactions between proteins. But finance, the World Wide Web, of course, is a graph structured healthcare field. So this type of data is unusually difficult to analyze using standard distributed memory architectures and other shared memory architectures. Okay, big data is the buzzword of the day. You know it's a buzzword when Dilbert's gotten a hold of it. He's done quite a few good cartoons on the big data phenomenon recently. I say at the database conference, 3 separate people chose that same comic to open up their talk, so I decided not to do it here today. But anyway, big data is basically started with the internet, but many other fields discovered that they have more data than they possibly know what to do with. That's sort of the unofficial definition of big data is too much data for you to handle. So Google, for example, Facebook, many other fields. And so the uRiKA appliance is targeted at, oops, that's not that. It's targeted at in-memory analytics, but some of the other fields are scale-out analytics, which is basically what you would call in the HPC world embarrassingly parallel data. So you may have heard of the Hadoop programming model and column stores. These are basically ways of using extremely large numbers of processors to do embarrassingly parallel work. Google is the best example of it. They invented the Hadoop algorithm, which is actually known as MapReduce when Google was doing it. So this is the embarrassingly parallel or horizontally scaled portion of the big data world. Another one is the more traditional data warehouses. These are the supercomputers of the database world. One example is the Oracle Exadata. These are what you would consider fairly powerful machines, but they're programmed as standard relational databases. And what uRiKA does that is unique is it works on graph-structured data. It uses a database type, which I'll explain later, which is inherently graph-structured, and it is an entirely in-memory database. So most databases are based on a large number of rotating disks, but in this case, since we have a very large shared memory machine, we store the entire database in memory, and as you can imagine, this leads to several orders of magnitude of performance improvement. And being able to do this relies on the unique characteristics of the XMT. So basically non-partitionable, which I'll explain later, graph-structured data sets, pattern matching and filtering across this data. And right now this is the only, well, it is the most high performance in-memory graph-structured database. Yeah?
I have a question about the use of the term big data.
Yes, I know.
Because when you look at the data that you have to blow up in memory, because you make a full graph representation, and then you run graph partitioning algorithms on it. That, but in the end, it's not such big data sets that you can that you can look at.
Right, and in fact, the unique feature of the uRiKA machine is that you do not need to partition the graph.
Okay.
And it is specifically I'll go into this in more detail later on, but some data sets are not easily partitionable. It would generate an extremely large amount of traffic and it would be highly inefficient. So if the data set is trivially or relatively easily partitionable, it can be done on a distributed memory machine. But this is a large shared memory machine. And many of in the previous slide, all of the fields that I showed there, the graphs are not easily partitionable. And so it leads to severe performance problems. So for example, in scale-out analytics, those are easily partitioned data sets. And that's why we think of that and that can be done actually, since it doesn't require a network, it can be done efficiently on clusters, and usually is cheap clusters. Okay, and that was basically an intro to the next slide. Current architectural approaches, basically Hadoop or the Oracle Exadata, result in very low performance on graph analytics problems for several reasons. One is that graphs are hard to partition. Every time you get an edge that crosses a processor boundary, it generates communication, of course. And so in the sort of graphs we're talking about, there might be 10 to 500 or 1,000 times as many edges as nodes. So there isn't any easy partition that could actually cut a minimal number of edges. No matter how you distribute your nodes, you will always end up with a large amount of cut edges and a large amount of communication. So it's possible, but it's extremely expensive to follow links interprocessor. Another thing that about graph data, in that it's extremely irregular, is that they're not predictable. And they're not. When I say they're not predictable, it's not that they're not deterministic. It's that they're very difficult for a memory controller to follow around the machine. When you're jumping from node to node, you can span the entire memory space of the graph in a single hop. And so since they're not partitionable, you also don't know. It's hard to know where your next memory reference is coming from, and as a consequence, these algorithms blow cache out all the time. They have almost no cache utilization, and so that's one of the strengths of the uRiKA system. Basically, cache-based architectures work very poorly on graphs. Another is that these graphs are changing very rapidly, and so you need a very, very high-performance I/O subsystem. And as you know from the other Cray machines that you own, we do have a very high-performance parallel file systems. You need to be able to load a new data set to fill the entire memory of the machine in seconds or minutes instead of days, which competing machines will often take. It can take several days to actually load a new data set, and we can do it in minutes. Okay, so the idea behind uRiKA is that it's an appliance, standalone appliance, both a hardware and software combination that is built for the graph analytics. And so I think the most important feature is the very large shared memory. The architecture allows up to 512 terabytes. Typically, the shared memory will be on systems we're selling is 2 terabytes to 32 terabytes. The architecture of the multi-threaded processor basically is entirely data cache free. It's one of the unique features of it. There's no data cache, so there's no worry about cache coherency. There's no worry about non-uniform memory access, cache traffic, things like that. And then finally, of course, we have the I/O subsystem. So the idea is that this offers an extremely high-performance machine for solving problems that have been very, very difficult for any other type of machine to solve. Any questions about what the idea is? I guess I should say the reason that we call it an appliance is that it actually comes with the software pre-installed. This is actually the first time that Cray has, for many, many years, since Cray research days, that Cray has sold any application software. Usually, as you know, you would think of us as a hardware vendor. We sell you the OS and the compilers and things like that. But this is actually a dedicated application built into a machine. So that's part of the motivation between the name of the new company and renaming the machine. Now, of course, you can load this software onto your XMT-2 and it becomes a uRiKA when it's running that application. Everything else still works in just the same way. Okay, so basically here's a summary of the appliance. There's the XMT-2 hardware engine. The original motivation for this machine was for graph analytics for the intelligence community. Has very large scalable shared memory, typical systems 2 to 32 terabytes, as I mentioned, and the unique multi-threaded processor. The multi-threaded processor is not only data cache free, but it uses the multi-threading approach to hide memory latency. So to the programmer, it appears to be uniform memory access to the entire machine. Okay, over the hardware engine, we built a multi-threaded graph database, which is a highly parallel in-memory RDF SPARQL quad store. And by the end of this talk, you'll know what that might be. We have very high-performance logical inference engine that's a necessary part of RDF and SPARQL, high-performance parallel I/O. And then finally, the most important part that makes it an appliance is that it's got an industry-standard front end based on open-source software. Of course, the multi-threaded processor is unique, but to the outside world, it appears to follow, we use a very standard open-source semantic database called Jenna, which was originally developed by Hewlett-Packard and then open-source. Everything else is standard Linux, so you can write Perl, Java, whatever you like. Most of the semantic database world is working in Java. And finally, we use Lustre, which of course is a industry standard. Okay, so that's an overview of the uRiKA appliance. Now I'm going to try to explain the multi-threaded processor. Some people in the room will have heard of the multi-threaded processor, or multi-threaded architecture approach. As you know, it's been around for 15 years, but the word is starting to become used again now with things like hyper-threading and many-core and things like that. But it still is quite unique. Okay, the motivation for creating the multi-threaded processor was latency was basically the mismatch between processor and memory, which you all know about, being HPC people. And there have been various approaches in the past. Vector processors, Cray's original product line, allocated large blocks and amortized memory latency with large regular data structures. Now, cache-based microprocessors take advantage of data locality to reduce memory latency. But a multi-threaded processor actually just tolerates the memory latency. It makes it, if you have enough parallelism in your architecture, in your algorithm, then it appears to vanish. And I'll explain how that works. So it works well when your algorithms are highly parallel and your data is, there is very little data locality. So what that describes is problems in graph analysis, semantic databases like the uRiKA, social network analysis. So it's uniquely well suited and the only machine of its type for very large graph problems. Okay. It's a new architecture, but I'll quickly try to explain it. On the left, we have a conventional processor. You can see you'll have a register set and a program counter, and then, of course, your arithmetic logic unit. This could be multiple pipes, whatever. And so a normal x86 or RISC architecture, this represents one processor. Now, on a multi-threaded processor, there are actually 128 sets of registers and program counters. So each one of these is known as a stream, and each stream can support multiple threads of computation. So it's a highly parallel architecture. And what happens is that with all of these different sets of hardware streams, the processor makes a context switch every single clock tick. So every time, basically, you swap in a stream, connect it to the arithmetic logic unit, and do some computation, and swap it out the next tick. And the reason that we do this is that if a certain thread of computation requires a remote memory reference, it is simply swapped out and not called in again. So we have two pools of threads. We have what's called the ready pool, which is the pool of all of those that have all of their memory references fulfilled. And those are swapped into the processor. It sort of rotates around between them. And then we have the wait pool. So if you have a remote memory reference, you swap it out from the ready pool to the wait pool, and then you send out a memory request, generate a memory request. When the memory request returns the memory subsystem, then it goes back into the ready pool again and is worked on. So basically, if you have a large amount of parallelism in your architecture, you can keep the processor pipeline filled. You can keep the ALU filled. So there's no worries about caches. There's no worries about branch prediction or any of the other things that bedevil modern processors trying to solve the same problem. In this picture, it looks as though you're simply spinning around between the threads in a rote manner. In fact, the algorithm is far more complex than that. But the thing to remember is that there is a ready pool of threads ready to go, and then a wait pool of threads that are waiting. So basically, the reason that we did this is to keep the bottlenecks in the machine saturated. So imagine a conventional processor working on a data set that has very, very little memory locality. So almost every memory reference will be out of cache. So while it's waiting for those out of cache, those cache lines to be filled, then the memory bus here is stalled, and the network bus here is stalled until that request is satisfied. So you get very poor processor utilization on data sets with no locality. Now, the thing about a multi-threaded processor is because it's constantly switching between threads, it is constantly generating memory references, both to its local memory and off on the network. And so you're making maximum use of your most precious resources, which are memory bandwidth and your network bandwidth. And the joke that we make about this is that it's basically a multi-threaded processor is a device for turning a latency-bound problem into a bandwidth-bound problem. So it basically trades off latency for bandwidth. And from the point of view of any individual thread of computation, since they're swapped out and in suspended animation in the wait pool, it appears as though all of your memory references are satisfied immediately. So it basically hides the memory references from the threads of computation. And thus you do not have, it's an entirely uniform and scalable memory architecture because the programmer does not need to worry about any sort of data locality, any sort of partitioning, just a huge shared memory pool, just like you always wish you had. So the programming model is actually all of the threads on the entire machine it basically forms one big bag of threads, and there's an interconnect network, and then a huge pool of absolutely uniform shared memory. So it's a very, very simple programming model. And we have the hardware was developed in parallel with a very clever compiler that automatically parallelizes C and C++ for this architecture and makes the whole thing work. So it's really a compiler and hardware combination that allows this to work. Yes?
How does the latency compare to a regular process?
Oh,
It's longer.
it's actually it's standard for an XT5. Most of your reference, since the memory is distributed, you're using all of the memory as one big pool. So it's roughly a little over a microsecond, the same as you would have with any of your other machines. And so that is hidden by the very large number of memory requests that are sent out. If you have one thing it does not work well on is serial workloads. If you have, and I'm not kidding, it's very slow on a plain serial workload because since it has no data cache, every single memory reference will take that same a little over a microsecond. However, for the right workloads, it actually offers very high processor utilization. And as I say, it can feed this very, very large and unique shared memory pool. Now, are there any other questions about this architecture? Because I know I just did it in 3 slides, but it's an entirely new type, and it's important. Understanding the architecture is important to understanding the rest of the system. An interesting thing about it is that in order to load balance the traffic on the network, memory references are in fact hashed across the entire system. So when you have a block of data, one word and the next word might be in different corners of the machine. So we deliberately make sure that there is no data locality. It's highly unlikely that you will hit memory on your own node even. But this balances, load balances out automatically. It is automatically load balancing, and it's basically automatically workload balancing, because it simply has a large pool of threads to call from and calls them in an entirely non-deterministic manner. Okay, so that was one piece of new technology that's already in the XMT-2. The next thing that we've added that makes it uRiKA is we've added a SPARQL database. SPARQL is a new programming language. It's similar to SQL, but it's developed for graph databases. And so we refer to it as a semantic database of RDF triples. RDF, which I'll explain in the next slide, is resource description format, and that basically is a way of describing a graph. It's inherently designed it was designed for the internet, hence the name semantic database, but it basically, at its core, is graph structured. And so these are often referred to as semantic graph databases. So you can see that it consists, here's an example of a very small semantic graph. So you can see that the nodes might be different objects or literals. So you have the country Canada. It's a directed graph, so there are relationships between all of these nodes, but it's inherently irregular. So you can see that Edmonton is an object. It's in the country of Canada, has the population 730,000, for example. And so this shows a very small, simple graph, but these graphs very quickly turn into millions or billions of nodes. Okay. So I mentioned RDF, or resource description format. The smallest atom of RDF, if you will, is a single RDF triple here. It consists of two nodes and one edge. It has a subject, a predicate, and an object. And so the subject, it expresses some relationship that the subject has to the object. And so even though it's a very simple atom, a large number of them can make up an arbitrarily complex graph. So it was, the original purpose of RDF was to enable machines or computers to search the web. I mean, we all search the web on Google or Bing or whatever you might choose, but web pages are meant to be read by humans. It's actually almost impossible for machines to read them. And so the idea behind this semantic web idea is that if you embedded this RDF in all of the web pages, then a machine could quickly make sense of the entire web. And so, though it came from the World Wide Web, we're actually using it as a database architecture so that you can make sense of irregularly structured data. There's the World Wide Web Consortium, W3C, that sets the standards, and then each of these subject, predicate, and objects are expressed as something called a URI. URI is a Uniform Resource Identifier. This is a superset of URLs. You know, when you're searching the web, it's called a URL. URIs are web objects plus file objects. So it's more complex, but you can think of them as web links if you like. And the important thing about them is they represent a unique object. Here's just a picture of some, there's the graphical picture of one triple. Here's what it looks like in a standard format. This is a gene. It's of type OWL. It is also a subclass of some other type of gene, and it also has the label, I can't even pronounce that word, but it sort of looks like the transmission line noise, but this is it's basically a very simple concept. Okay, now RDF is the way the semantic database is expressed. The way that you query this database is the language called SPARQL. It's related to SQL. It sort of looks like SQL. In fact, it behaves quite differently. But it enables the matching of graph patterns. And so the core algorithm of uRiKA is basically a subgraph isomorphism algorithm. You, using the SPARQL language, create some sort of pattern that you'd like to find in there. And I'll explain this example in a second. And the machine goes out and finds it. So in this case, this is a benchmark called Lubbock Lehigh University benchmark. The benchmark describes a whole series of universities that have students and professors and papers and things like that, and all the different relationships between them. As you can imagine, universities are quite chaotic, so it's graph-structured data. And so what this SPARQL query represents is show me all of the students in the university who are taking courses from their faculty advisor. And so this is actually a very, very difficult query for a standard database because it looks like a triangular pattern with 3 implicit joins. And very, very slow on a standard database, but extremely fast on a semantic database. So you can you define X, Y, and Z. X is a student, Y is a faculty, Z is a course, X is the advisor of Y, Y is the teacher of Z, Z the class, and then the student takes the class. And as you can imagine, this creates a little triangle. So the language is far more complex than that, but most of it is basically searching these graphs at extremely high speed and locating these patterns. Okay, so that's a quick introduction to SPARQL. Are there any questions about this? I think I'll go into some use cases in a moment to show you how this sort of programming model might be used. But it's basically a new language. It's an industry standard language and industry standard data representation. And it's coming to the fore as the standard for dealing with this type of database. And particularly graph analytics over this type of data. Okay, here's a more detailed description of the appliance itself. This graph analytic platform here is actually the XMT-2, which we just saw in the machine room. Above that, we have the database, which was developed by Yarc Data, which is the RDF data store and the SPARQL query engine. On top of that, we have database management tools. On top of that, we have the Jenna semantic database. We use Tomcat to talk to the web. And you can address this in any of your standard languages. So basically, it looks to a data center like a standard Linux server. You can use all the open source software tools that you're used to for working with semantic databases. And so you can also, there's no vendor lock-in. Anything that you can run on uRiKA, you can run somewhere else. You can download the, I'll have a link at the end. You can actually download the Jenna database to your laptop, and you can actually do development of queries and small data sets on your own computer. And then when you have them working, you can move them up to extremely large data sets on the uRiKA. So it's quite industry standard, and that makes it useful for prototyping. Okay, here's a functional view of what it looks like inside. This is a SPARQL query. It's a bit hard to see because it's gray on white. This comes from some external application. So there's a SPARQL query. There are various types of SPARQL ingest applications. Some of them are graphical, some of them are text-based. Some of them are automatic parts of pipelines. But basically, it takes a SPARQL query and connects it to the Jena database. So the Jena database generates a low-level query. It does some parsing of SPARQL and sends it over to this API. Now, something that's unique about this machine is that the service nodes, and it's a hybrid supercomputer, and so the service nodes and the compute nodes are completely different architectures and even different endianness. So, and they also have two different operating systems. So they're very, very, very different. And so we have to have an API that crosses that. But as you're used to with your current machines, the service nodes and the compute nodes are on the same C-star network. So basically, the query is sent over to this API. It's parsed and turned into an intermediate representation, and then given to this SPARQL engine. These are basically terms that you'll see in a SPARQL query. Each one of them is extremely highly parallelized, and it's basically an RPN-based selector that calls all of these multi-threaded algorithms, and then they go to this database. Now, the database is just shown as a single column. In fact, it's far more complex than that. There are reference arrays. It is hashed across all of memory by the hardware, so it's just simpler to draw it as a single column. I'm pleased to say that I wrote the SPARQL engine, which is probably why they sent me out here to talk to you about it. But so are there any questions about uRiKA? It's basically very straightforward. Okay, and uRiKA is basically meant to be used as part of a pipeline for analysis. Though it certainly can be used standalone. Most of the customers that we talk to actually already have an existing data warehouse. Many of them have Hadoop clusters, et cetera. And however, they have graph analytic queries that their other machines simply can't handle. So uRiKA enables them to work with, back and forth with their other big data appliances. It's actually fairly similar to the way that it's installed here at CSCS, and I've used you as an example. You have a large shared memory Lustre file system that is shared with several other big data machine types. So you can use, for example, if you have some embarrassingly parallel work that's quite large, you can put it on Hadoop, and then take the results, put them into uRiKA, store those results back into Hadoop for other processing. Okay. One of the things that we've not removed is that you can still program the uRiKA as a C++ highly parallel supercomputer. So the existing programming environment is still there. It consists of a automatic automatic parallelizing C++ compiler that I mentioned. It actually, with just a few compiler directives, will automatically parallelize your code. So for this multi-threaded system. So I know that in the supercomputer world, the so-called automatic parallelizing compiler is widely felt to be a myth, but within this architectural framework, it does a very good job. Login nodes, service nodes you're used to. We have an interface library that forms that API, and then finally Lustre, which you know about. One of the clever things about it is that when you generate a binary on the XMT or uRiKA system, a complete runtime is attached to every single binary that you generate, and it is actually responsible for all of the mapping to the actual hardware, handling the streams, et cetera, thread management, hardware traps. So it's a very unique shared memory distributed operating system with a lot of the intelligence actually built into this runtime attached to each one of your jobs. And say provides support for profiling, client-side debugging, et cetera. The Appliance-2 tool set is available, which you're used to, is available on this machine also. And there are some new reports in Appliance-2 that are specifically for the for the XMT or uRiKA architecture. I won't go into these at depth. You can ask me about the different tools. It'd take several more hours to describe what they're for, but basically it's profiling, tracing, and compiler feedback. Okay, so I know I've presented some fairly new concepts, the multi-threaded processor and the SPARQL database, and I'd like to describe how they might actually be used. This is one of the use cases that I've been working on with a Cancer Research Institute. I can actually say that that is the Institute for Systems Biology in Seattle. It's Leroy Hood's group, very well-known group, that are basically trying to uncover new cures for cancer using systems biology. So the problem that they had is that they had very large data sets describing biological networks in cancer cells, both from published literature, experimental data, et cetera. And the network of relationships between the genes and all of the different relationships that were known about them form a densely connected graph. There's 440 edges for every node in the graph. So it's quite non-partitionable. One of the big problems that they have is that there are massive quantities of literature. Over 10,000 genomics publications are produced per month. And so in theory, if you're a scientist working in this field, what you do is you want to read the papers, you'd want to look at your experimental data, maybe look at some databases, and try to draw conclusions. But the amount of data is just too large. It's more data than you know what to deal with, 10,000 papers a month. And so the publications are, all of this data is converted into RDF triples, and then you can search for patterns that might be clues for cancer. So basically you have this large unpartitionable network, holds it in memory, and enables you to do rapid querying across it to test new theories. So from a technical point of view, the source of the data is something called the Cancer Genome Atlas. And this is literature, which the Cancer Genome Atlas is experimental data and known technical data about genes. They take the literature from Medline, which is basically all of the medical data that is published about cancer. That's the 10,000 new publications per month. And then there are large protein databases called Uniprot, PFAM, and others. So what you do is you take all of these different databases, which have come from different sources, you express them in an RDF format, and then create a very large graph. And then you can do SPARQL queries across that graph. So in this case, we have 1.2 billion entries in the Cancer Genome Atlas, generates 6 billion triples. We're adding more data sets all the time, so this use case is growing and growing. And they were absolutely unable to query this on any of the other database technologies. So it's a very useful thing to be able to do, to be able to find patterns in all of this data. And uRiKA is actually the only machine that can do it. So another use case that is very important to us is financial services, trade surveillance. Basically, there are a lot of rules about how you can trade. You've all heard of insider trading, and there's a scandal every once in a while where people are getting information they shouldn't about stock trades. And so you basically have to find out all the relationships between all of these stocks, all of these stock traders, all of these other players in the stock market. And there are relationships between all of them. Which are changing all the time. Some of them, someone might make a phone call to someone else. Two people might show up at the same restaurant at the same time. There are there's a very complex web of relationships, and you have to look for patterns of relationships that would indicate insider trading. And there are very strict rules about how this is done. And so this is essentially an impossible problem. And for standard technologies, but it can be solved with a semantic database. Another good example is you remember the large financial crisis of 2008. One of the one of the reasons that it happened is that many of the financial instruments that were generated are too complex for anyone to understand. There's basically no way of analyzing all the complex web of interconnections between all the things that are gathered together in a financial instrument. And so that's another one of our use cases. I don't have a slide for it, but we'd like to think that if they had some of these systems back then, they would have prevented the financial collapse. Okay, I'm exaggerating a little bit, but another use case is market sensing. Basically, there's a lot of data that comes out about things that happen in the market, news articles, bits of information, and they might relate to a large number of different things. And so you want to be able to trade based on what's happening out there in the market, but you want to do this in real time, and the data is quite complex and quite interrelated. So you're able to hold an entire model of all of these market factors in memory, and then see how they might affect one another. The example that we give is that everyone knows about the big floods in Thailand resulted in a severe shortage of disk drives, and so disk drive company stocks went down. Something that few people realize is that stocks in Caterpillar heavy equipment also went down too. And I don't even know why, but it turned out that through this complex web of relationships, there are influences. Another very useful case is in the healthcare field. I can actually say here that we're working with the Mayo Clinic, a very well-known hospital group in the United States that does very advanced research. And basically they're looking at a way of optimizing treatments by finding cohorts of similar patients. And the idea would be that they're working on developing this now. They have one of our machines. And a doctor might have an iPad and be standing by a patient's bedside and asking him questions and plugging in data off of his chart. And then they will go to this huge background database of genetics, family history, all of the medical records associated with that person or with anyone that the hospital has ever seen to try to find a cohort of identical individuals and find out what treatments they responded best to, what drugs they might have had reactions to. So this is a very, very important thing for the hospital because it allows you to optimize treatment and make use of, make extremely rapid use in minutes while you're standing at the patient's bedside to figure out the best course of treatment. And for a standard database or any other analytic technique, it might take weeks to actually prepare a cohort of this type, but this can be done interactively using the uRiKA machine. Am I getting towards it? Okay.
Any questions?
Any questions?